Hi, this is Professor Sugard, and in this lesson, we're going to be talking about tangent planes. So, tangent planes are basically taking our idea of local linearity from Calc 1 and extending it to Calc 3. So if you remember, back in Calc 1, local linearity meant that if I have some curve, if I zoom in closer and closer and closer to that curve at one specific point, that curve is going to start to appear like a line. Right? So it might look all curvy when I look at the whole picture, but again, if I zoom in really close, it's going to look like a line. Well, tangent planes work the same way, except with surfaces now in R3. So even if I have some sort of curved surface, like I have in my picture, if I zoom in, well, that surface is going to start looking a bit flatter. And if I zoom in again, it looks almost flat. And that is what my tangent plane is going to be. If I zoom in really close to a surface, it's going to start to appear flat, and that flat surface is my tangent plane. And we actually see this idea in real life quite a bit. We live on planet Earth, which is a giant sphere in space, which is, well, quite round. But if you zoom in really close to the surface, like, let's say you're a human standing in the middle of a desert, well, even though the Earth is completely spherical, it's going to look quite flat if you're standing by yourself in a wide open area. Well, does that mean the Earth is flat? Well, no, but you could forgive someone 6,000 years ago for believing the Earth was flat. Today, well, not so much. We probably shouldn't forgive that as much, seeing as how the ancient Greeks proved the world was round, over 5,000 years ago. And then you have the ancient Greeks actually visiting Egypt who were able to calculate the radius of the Earth within 1% of its actual radius. And that was well over 2,000 years ago, which is quite impressive feat. But again, the idea is that these curved surfaces, if we zoom in, it's going to look flat, and that flat surface is what my tangent plane is. Now, to define it a little bit more rigorously, the tangent plane to my surface is actually going to be all of the tangent lines to the surface at that point. So again, if I have some point on my surface and I calculate all of the tangent lines to that point, all of those tangent lines together form my tangent plane, infinity many of them. Now, the nice part is I don't have to find infinity many tangent lines to find my tangent plane. I'm just going to need two tangent lines. In this case, I'm labeling them tangent 1 and tangent 2, or T1 and T2. And hopefully you can kind of see from this picture that they're definitely going to be related to my partial derivatives, because it looks like T1, my tangent line 1, well, that looks like that's going to be in my plane y equals some constant. And tangent 2 is my tangent from, well, looking at the plane x equals some constant, which, oh yeah, those are my partial derivatives. So let's actually take a look at the rigorous mathematics and how we're actually going to define it. So first of all, we're going to start with our equation of the plane, our scalar equation of the plane from our previous sections. And what I want to do is try to solve this for the variable z. All right, so if I want to get z by itself, I'm going to divide each term by c. All right, even the other side of the equation. But obviously 0 divided by c is just, well, 0, so that's not going to change anything. C divided by c cancels, and then I have my coefficients here. Well, then I'm going to subtract my x and y terms. So if I subtract them from both sides, they'll become negative. And then just to make life a little bit easier, we're going to substitute. Instead of having negative fractions, let's just get rid of the negative fractions and call them a and b, because it doesn't particularly matter. A constant is a constant, right? A constant plus a constant is still a constant, or a constant divided by a constant is a constant. So again, just to simplify things a little bit, to make it look a little nicer, there we go. That's the equation that I want to start with. Well, once I have my equation, I want T1 to be that tangent line from the trace in the plane y equals y0. So again, I have my point on my surface, x0, y0, z0. And I want T1 to be that tangent line in the trace y equals 0. So that's, again, that plane where y equals a constant. And again, it's going to intersect at that exact point, which hopefully makes sense based on that picture. But when I do that, if y equals y0, well, if they're the same, then up here, that whole thing is going to go away because, well, y minus y0 is then equal to 0. So you're just left with the other part of the equation. So z minus z0 equals a times x minus x0. And maybe you're seeing this already, but this is our point slope form of a line. Now, in this case, our slope is given by a, but it's definitely the point slope form of the line. Take a second, look at it, and be like, oh, yeah, I remember how to do that because I remember doing tangent lines back in Calc 1. But if that's the slope, well, wait a second. We said T1 was the trace in the plane y equals y0. From our section of partial derivatives, we know that that has then got to be the slope of the tangent line with respect to x, which is the partial with respect to x, which means a is really the partial with respect to x evaluated at that point. Now, we make a very similar argument for T2 being the tangent line on the trace of the plane x equals x0, and so b is really the partial derivative with respect to y evaluated at that point. And we get our formula for the tangent plane. And this is the formula we follow to find the equation of a tangent plane. And again, the thing to remember, though, is with this really complicated formula, this whole quantity here and this whole quantity here are really going to be the constants. Those are really those a's and b's. Those are slopes. Those are going to be actual values. So when we use this formula, we better be plugging in actual constants, actual values, actual numbers in for those two expressions whenever we do the problems or our homework. And I will point out that that is a very common mistake that I see when going over the homework, is that students plug in the partial derivative. They forget to plug in the partial derivative evaluated at that point. So again, it is the partial derivative, but it's the partial derivative evaluated at that point. And so again, you might see the notation simplified to just this because, well, admittedly, that second line just looks nicer. It's not nearly as cluttered, but you might forget to actually plug that point in if you're not paying close enough attention. So again, just be really careful. Make sure you're actually plugging in for that value. And so let's do an example where we have to plug in for that value. So let's say I'm given a surface where I have the quantity x plus 2 squared minus 2 times the quantity y minus 1 squared minus 5. And I want to find that tangent plane at the point 2, 3, 3. Well, first things first, let's calculate and evaluate our partial derivatives. So we'll start with the partial with respect to x. So my partial with respect to x, well, here's the only part that has an x in it. And I should be able to take that derivative pretty easily using the chain rule. So bring the 2 down in front and then take the derivative of the inside function, but well, it's just going to be 1. So my partial derivative with respect to x is 2 times the quantity x plus 2. And again, this is the key, evaluated at that point. So if I plug in a 2 for every x, a 3 for every y, and a 3 for every z, well, really all I'm plugging in is going to be the x anyway. But when I plug in the 2, my partial derivative with respect to x at that point is going to be the value 8. Then we do the same thing with the partial derivative with respect to y. And again, that's this whole part. So bring the 2 down in front. So negative 4 times the quantity y minus 1. Evaluate that at the point. And again, plugging in the value. In this case, we're only really plugging in the 3. But we get the value 8. So again, those give us our f partial x and f partial y evaluated there. And I have 8 and minus 8. And so we're pretty much done. Now that I know what those values are, I can plug those in here and here into my formula. I know my point. So I have my x0, y0, z0. I plug everything in. I distribute. I get everything. I kind of group my like terms. And I get my answer. Now again, hopefully you're following along. You're writing this out yourself. And hopefully you got the same answer as me. 8x minus 8y plus 11. That becomes my equation of the tangent plane. And I recommend that you actually go on GeoGebra and graph both of these functions. Graph my first function z, graph my tangent plane, and make sure it's actually going to be my tangent plane. Take a look, play around with it yourself. Actually gain an intuition for what's going on here. It will absolutely make life way, way easier when we get to chapter 15 on our integrals. Just saying. Now, why are tangent planes valuable? Well, they're valuable for lots of reasons, but one of the reasons is that we can use them to make approximations. And just like we can use the tangent line to make approximations about our curves, we can also use tangent planes to make approximations about our surfaces. Again, typically around just one point. And just like we had that definition back in Calc 1 for linearization, well, the tangent plane is our linearization of our surface, just like our tangent line was our linearization of a curve. And we're still going to use capital L, the function capital L, as a way to represent our linearization, which again really just means our tangent. So the linearization of a surface is L of x and y. All right, so given a surface, and we're actually going to be using the same surface from example 1, I want to approximate what my function would equal for x equals 2.1 and y equals 2.9 using that linearization around x equals 2, y equals 3. Well, again, this is the same function from example 1, and my x and y coordinates are the same for x equals 2, y equals 3. So my tangent plane, or my linearization, is the same one as I found before. Z equals 8x minus 8y plus 11. So there's my linearization, right? So L of x and y is my 8x minus 8y plus 11. So if that's my linearization, all I have to do is evaluate now at my point, 2.1, 2.9. So plug those in, follow the order of operations. My linearization gives me the value 4.6. Now, this is the approximation. I approximated that the value of my surface at that point is 4.6. I can go back and evaluate the original function too. This is really not a difficult function. If I actually plug in those ordered pairs for x and y, I get the actual value, which is 5.4 or 4.59, sorry. So hopefully we can see that our approximation and our actual value are pretty similar. And you might be asking, well, that was really easy just to plug in the values. Why am I doing an approximation here? And really the answer has to do with computers. And being able to approximate surfaces using nice, neat tangent planes is actually way, way, way more efficient on a computer than actually evaluating surfaces. So my tangent plane, right, when I did my actual approximation, all I had to do was multiplication and addition. That was it. I had to multiply twice and add 3 different numbers together. That was it. And I found my approximation. And a computer can do addition and multiplication incredibly quickly, in the blink of an eye, even faster. However, computers are really, really slow when it comes to things like exponents or radicals or exponential functions. And if you're trying to make make graphics, right? Make computer graphics, well, if you have to keep rendering surfaces in 3D, so let's say you're trying to, make a video game, right, with a 3D environment or a VR environment, well, you want to make your surface and you want to display your surface, but to have the computer run through the calculations to actually create your surface, that is incredibly inefficient. It's going to take forever, and your game is going to run incredibly slowly. However, if you can approximate that surface using tangent planes, which only use addition and multiplication, the calculations go incredibly faster, and you'll actually be able to render your 3D environments in real time so that, well, people don't necessarily notice that they're playing, pixels on a screen. You'll actually be able to create that illusion of having moving surfaces. All right, so time for a theorem / definition. They kind of go together here. Your book calls it a theorem, so I will as well. But given a function of 2 variables, z equals f of x and y, if those partial derivatives, partial with respect to x and partial with respect to y, if they're continuous and they exist near a point AB, then we say that function is differentiable at the point AB. Now, What that really means is that as long as that function is differentiable, that means that the tangent plane actually would be a good approximation. And so you want to be careful because not every function is necessarily differentiable, so you wouldn't be able to use a tangent plane to approximate necessarily every function at every point. But basically, as long as you could do the process to find the tangent plane, well, you'll probably be okay using the tangent plane as your approximation. The last idea has to, again, do with optimizing functions and determining, in this case, a way to approximate the increment. So the increment of a function is basically how much it changes. So the idea is that as I change from my ordered pair xy to some ordered pair where I'm moving over a distance of delta x and a distance of delta y, well, delta z, that change in z, is going to be the difference of my function evaluated at that 2 points. So evaluated at point 1, evaluated at point 2, find their difference by subtracting, and that's your difference in z. That's your change in z. That is your increment. So again, the formula looks more confusing than what it's actually saying, but that's the idea. There's your increment. That's how much your function is actually changing. The differential is typically a much quicker way to approximate that value. Again, if you have to do this approximation hundreds of times or thousands of times or even millions of times, well, doing it by finding the increment could be incredibly, computationally intensive. The differential, on the other hand, should make it a little bit easier. And so the differential is given by dz. So again, we're using dz here. And it's the partial with respect to x. And again, you might see that partial with respect to x given in two different ways. And then dx. Now again, make really careful note. When I do my partial, it's that del notation, right? That's definitely my partial notation. Whereas d is my traditional derivative, meaning that there's only one variable there. And we're going to talk about this again. The same exact function is actually going to come up in our next section on the chain rule, but it's important to make a note of it now. And then again, when we have the partial with respect to y, again, I could write that as partial z, partial y instead. It's the same idea, just slightly different notation. And then, of course, the d in front of the dy means that there's only one variable. And again, I'm going to do an example, and hopefully that becomes a little bit more clear what we're doing. And again, that main idea that the differential is our approximation of the increment. So given a new function, in this case, let's give our function as z equals 5x squared plus y squared, and my ordered pair is 1, 2. I want to calculate what's the increment and what's the difference in my function z as I move from the point 1, 2 to the point 1.05, 2.1. All right, so we'll calculate the increment first. And again, it's going to seem really silly if we are only doing this one time, which is all we're doing for this particular example, because it's going to be really easy. Just plug in the ordered pairs into the function, let your calculator evaluate them. It'll happen in about half a second. And so my function evaluated at 1.05, 2.1 is 9.9225. And if I evaluate it at the ordered pair 1, 2, I'm going to get the value 9, which means the increment is the difference. The increment is the 0.9225. All right, now we can approximate with the differential. And so it's going to be a little bit more work up front, but remember, if I had to do this operation a million times, well, this differential would make life way, way easier. So I have to find my partials. Now, the partial with respect to x of this function is pretty easy because there's only one part that is an x. The partial with respect to x is, well, 10x. The partial with respect to y is 2y. The other part I want to keep track of is going to be my dx and my dy. And so my change in x, well, going from 1 to 1.5 is an increase of 0.05. My increase from going from 2 to 2.1 is an increase of 0.1. So I have those parts set aside now as well. And then we need to evaluate this differential at my original ordered pair. So my original ordered pair is 1, 2. And if I just plug in x equals 1 and y equals 2 into my two partials, well, that's pretty straightforward. The partial with respect to x is just 10. The partial with respect to y is just going to be 4. And again, the idea is I'm plugging in those values into my partials that I found. Well, now I can plug everything into my differential equation. I'm replacing my partial with respect to x is 10, my partial with respect to y is 4, and then my dx and my dy. Now, again, typically you would be swapping out the dx and the dy for your thousands of different values around that point to get an idea of the increment, but we're evaluating at just this one point for this example, and we find that our differential is 0.9. Well, remember, our actual increment was 0.9225, so our approximation isn't that bad. I mean, it's off by a little over 2/100ths of a unit, but, you know, when you're doing approximations, that's good enough. And it's many times better to be quick than it necessarily is to be perfectly accurate. And again, that happens a lot with anything where you're using lots of amounts of data. And again, in engineering or numerical analysis for economics, or data science and machine learning when you're trying to optimize your function, again, going for perfect accuracy is going to be way more difficult and way more time consuming than necessarily just, well, approximating. All right, so that really finishes up all we want to talk about with the tangent planes. Like I said, this idea of differentials, we're going to see it come up again with the chain rule, and then we're going to see it come up again with a few other things that we do later on, and of course it's all going to be connected. But give your homework a shot. If you have any questions on tangent planes, please feel free to send me an email, and good luck.